Okay, in this video, I want to talk about bijectivity and how this relates to the important concept of being able to find the inverse of a matrix. The inverse of a matrix or the inverse of a linear transformation. Okay, so first of all, remember bijectivity. So if L is a linear transformation from Rn to Rm, it is bijective if it is both injective and surjective. Okay, so if it's injective, this tells us that in is less than or equal to m. If it's surjective, this tells us that in is greater than or equal to m. So it's injective and surjective. That the only way this can work is if in is equal to m. So L is going to be a linear transformation from Rn to Rn. So that red in used to be a green in. So L is a linear transformation from Rn to Rn, and it's going to be a bijection. So let's think about what some of this stuff means here. Okay, so this means that the equation LV equals W, well, it's injective, so there is at most one solution. It's surjective, so there is at least one solution. Since it's both, it means there's exactly one solution. So this has exactly one solution for all W in Rn. Okay, so what this means is that for every W in Rn, there is a unique vector in Rn that satisfies LV is equal to W. Okay, so this means that we can define an inverse transformation. This means there is an inverse denoted L inverse, or L to the power of minus 1, meaning L inverse, that satisfies the following equation, or the following facts. LV equals W if and only if V is equal to L inverse W. Okay, so basically L to the power of minus 1, this is just a symbol. Okay, it's a transformation that satisfies this property. There's a transformation L inverse, or L to the power of minus 1, that satisfies LV is equal to W if and only if V is equal to LW. That's sort of one way to think about it. Another way to think about it would be, well, I guess, okay. Another way to think about it would be to say this, that a solution to LV equals W is V equals L inverse W. Or another way, what we're really just doing is multiplying both sides of this purple equation by L to the minus 1. So L to the minus 1 LV is equal to L to the minus 1 W. Okay, and really what we're saying here is that L inverse times L applied to V is just equal to V. Or another way to say this would be that L inverse times L is equal to the identity transformation. Okay, these are all different things, different ways to say that L inverse is the inverse. Okay, now there are a couple of things to say. One, L inverse is linear, and L inverse is a bijection. Okay, and for now, I think y'all are okay with just taking that, taking my word for it, but I really think you should try to prove this. Try to prove that it's linear and try to prove that it's a bijection. Okay, so in terms of matrices, how can we find L inverse? So if M sub L is the matrix, if M sub L is the matrix for L, then what is M sub L inverse? In other words, given the matrix for L, just given the matrix for L, can we figure out what the inverse matrix is? Or the matrix for L inverse is? Okay, and remember in the notes, I told you how to do this. You start by row reducing this matrix. So it's an augmented matrix. On the left-hand side, you have the matrix M, or I'll write M sub L. And on the right-hand side, you have the identity matrix. Now you're going to row reduce this until you get the identity matrix on the right-hand side. So in other words, you're going to put M sub L into reduced row echelon form. And then the matrix that you have on the right-hand side is going to be the matrix for L inverse. Okay, so let's ask this question. How do you know the row reduced echelon form of M, or M sub L, is the identity matrix? Okay, well, to know that, you have to use the fact that it is both injective and surjective. Since it's injective, there's going to be no free variables. Okay, since it's surjective, there's going to be no row of zeros. So this tells us we're going to have no zeros on the diagonal. When it's in row echelon form, there's going to be no zeros on the diagonal. Okay, and then once it's in row echelon form and you know there's no zeros on the diagonal, then it's this easy, if you think about it, to see how you continue to do row reduction to get that matrix into the identity matrix. Okay, but the only reason that you can do this is because the columns of M form a basis. Since the columns of M form a basis, you can row reduce it to get to the identity matrix. And then the matrix that you get on the right-hand side of that is going to be the inverse matrix for L. Okay, so this is all part of something called the invertible matrix or the invertible transformation, or it's all related to the invertible matrix or the invertible transformation theorem. So let me just say one more time, or let me give one more definition. A matrix M is invertible if there is another matrix denoted M to the power of -1 such that M times M inverse equals M inverse times M, and this is the identity matrix. Okay, and here we're assuming that M is an n by n matrix, like we have been. This is an n by n matrix. Okay, so it's invertible if and only if there's this other matrix called M inverse, such that when you do the matrix multiplication, you get the identity transform. Okay, and the idea is that M is going to be associated to some linear transformation L, some bijective linear transformation L, and M inverse is going to be the matrix for the inverse of that. Okay, so you have an L, you can go to the matrix M, you can think about the inverse transformation L, you have an M inverse transformation, okay, or a matrix for M inverse. Okay, and now the idea is that the M inverse, that the matrix M inverse that goes with the transformation L inverse is going to be the matrix inverse for M. Okay, so L goes with M, L inverse goes with M inverse, and what we're saying is that M times M inverse go together, that they are matrix inverses of each other. In other words, it satisfies this equality here. Okay. And that can be seen by some of the stuff that we talked about in class. I'm not going to go over that again here. Okay, so the invertible matrix theorem, or the invertible transformation theorem, this is theorem 2.4, or 2.40. This is the invertible matrix theorem, or the invertible transformation theorem. It just gives a bunch of different equivalent statements for the transformation or the matrix to be invertible. Okay, so a matrix is invertible if an inverse exists. Okay, so here are some equivalent conditions. Basically, we've seen all of these before, but now we have it in one spot. So let L be a linear transformation from Rn to Rn. Then, and let M sub L be the matrix. Okay, then the following are equivalent. Okay, so TFAE is an abbreviation for the following are equivalent. So 1 would be that L is invertible. Okay, 2 would be that M sub L is invertible. Three is that LV equals W has a unique solution for every W in Rn. Okay, that was, why is that? Well, that's what it means for L to be a bijection. Okay, and the next one would be the same for M. MLV is equal to W has a unique solution. And why is this true? Well, this is true. This is true because if L is injective, the columns of M, L are linearly independent. If it's surjective, the columns of M, L are a spanning set. So in other words, we can row reduce M sub L to the identity matrix. So we can compute its inverse that way. Okay, being able to row reduce M to the identity matrix means that we can always uniquely solve the equation MV equals 1, 0, 0, 0, 0, MV equals 0, 1, 0, 0, 0, and so on and so forth. Okay, and this is equivalent to the columns of M being a basis for Rn. Okay, 5, there is, sorry, I kind of have it out of order than what I have in my notes. 5, the columns of M form a basis for Rn. 6, the columns of M are linearly independent. The columns of M are a spanning set. Okay, so remember that if we have n vectors in Rn, then if they're linearly independent, then they're a spanning set. And if there's a spanning set, then they're linearly independent. So if you know they're linearly independent, then that means they're a spanning set, and so that means they're a basis. Okay, so I'm not going to write those down. M can be row reduced to the identity. 7, M has n pivot columns when row reduced. When in row echelon form, I'll say. And 8, MV equals 0, has only the solution, V is equal to 0. Okay, that just means that M is an injective transformation, but since it's injective, well, that means M is an injective transformation, which means the columns of M are linearly independent, but since it's in vectors in Rn, that also means they're a spanning set. So that also means they're a basis. Okay, so this is just one short little interpretation of the invertible matrix theorem. Okay, so really you need to just spend some time thinking about this theorem and thinking about why it's true. Okay, I'm going to do some examples in a moment where I come up with inverses of linear transformations or matrices and just illustrate what that means a little more. But read through this theorem and understand why all of these things are equivalent to each other.